Thank you everyone for being here. So yeah, today I'm going to talk about this new machine we have at Argonne, Aurora, that is built with these new Intel GPUs. So this work has been done by people at Argonne, Colin, Thomas, Swan, and I, and also in collaboration with Kevin for AMD GPUs comparison. So just to give a brief overview of the current landscape on supercomputers, on the top 500 November 2024 list, there is, here you got the number of systems that are running AMD, Intel, and NVIDIA GPUs. Second line is the portion of that GPU system how they distributed among vendors. And the last line is on the computational throughput. So how to read this is, for instance, Intel is providing 4 GPU systems that represent 2% of the total GPU systems for 11% of the computational throughput. So the motivation of this work is, as Intel recently joined the market of GPUs, we wanted to evaluate how they perform, and particularly yes, on the Aurora system that is a result of several years of work with the Argonne facility. I may refer to the GPUs as PVC, that's the original code name. Here is an overview of the programming model used on Aurora. That's from a survey conducted in 2024. So as you can see, OpenMP is quite prevalent with about 23% of applications running it. And even for Cocos, I think the backend is mostly OpenMP. So this Cocos part may also be counted as part of it. You may be surprised seeing HIP there. We have some people using HIP, and we have that Chipstar runtime system that implements HIP on top of level 0. So HIP applications may run on Aurora. And so the implementations I'm going to evaluate today is Intel's implementation that was provided with the machine, which is open source here. So that's not the mainstream IIM. So that's an overview of today's presentation. I've just gave a brief overview of the HPC landscape and OpenMP at Argonne, how is it important. Now I'm going to give a brief overview of the Aurora supercomputer and the compute net architecture, and then present our evaluations on both compliance and performances. So here is a really large overview of Aurora's compute nodes. So there is 10,000 of these in the supercomputer. I'm only showing here computational units, so GPUs and CPUs and memories. There is also 8 NICs added to that are not shown here. So as you can see, there is here the 2 CPUs. So these are Intel SPR, 52 cores, I think. They have 2 memories, HBM and DDR5 with different boundaries that are shown here. They are connected through PCIs to GPUs. So there is, I believe, 1 PCI per GPU. It's not really well shown here. And then each of these GPUs, so there is 6 of them, are in fact 2 GPUs themselves. So one GPU is 2 stacks that have their own HBM. And so these 2 stacks are interconnected with a fast link that is 200 gigabytes per second unidirectional. And then each stack may be connected to another stack from another GPU, maybe non-uniformly. Like for instance, as shown here, the stack 0 is connected to stack 0 on GPU 1, but may also be connected to stack 1 on GPU 2. So it's kind of like this. So these things are fairly slow, the link between stacks, but there is many of them. Here is only shown 5 from the GPU 0 to all the others, but every other GPU is also connected to every other, like it's an all-to-all connection. So there is 15 links overall. So that's the large overview. Now if you look a bit at metrics, so yeah, those SPR CPUs are 52 cores, 2 stacks per GPUs. Each stack is made of XE core. They got 64, but not all of them are actually turned on due to energy consumption. Some of them are turned off actually. I think there is like 56 of them actually turned on. We got some metrics on performance, like the full GPU is 23 teraflops per second on that's a gem. We can compare that, for instance, to 800, that's right here. So it's about 10-20% more performance than 800. We got some metrics on memory, bandwidth, latencies. The one that I think is quite interesting is this host-to-device latency. So that's the equivalent of a CUDA copy if we do that in level 0. We get sub 1 microseconds to submit something and get notified on the host that this has been submitted for a single byte. So that's quite lower than what we would get on NVIDIA GPUs. I don't have, well, actually don't have any metrics here, but it would be, I think, more in the order of 5 microseconds, 6 microseconds. Yeah, I think that's it for this slide. Now is a brief overview of, so I presented hardware, now is a brief overview of the software. So the OpenMP implementations I'm evaluating is the one provided by Intel, packaged within the OneAPI toolkit. So when targeting GPU, there is two targets, one that is compiled just on time and one that is compiled ahead of time. There is two backends, so that's LLVM-based implementation. So we can select two backends for the target plugin, one using the level 0 native driver and one using unified runtime. Unified runtime is Intel attempt to make sort of a portability layer on top of level 0 CUDA. But we are not evaluating this because it was preliminary work back then when we did the evaluation, and it was not well supported by this OpenMP implementation. Then in the software stack, we can also specify how we want the software to see the GPUs, so whether in flat or composite mode. So in flat mode, every stack as shown earlier, the two per GPU will be seen as a single device. Or in composite, both stacks together will be merged into a single GPU. So in flat, we are seeing 12 GPUs. In composite, we are seeing only 6. Right. Intel OpenMP also provides this feature, which is implicit scaling. So the idea is if we are running in composite mode, if the programmer do an alloc of a straight array like this, it will be split between the two HBM of the two GPUs. So that's from Intel documentation. So the yellow part will be put on the stack 0, the red one on the stack 1. So it's like uniformly split between the two. And then when we do some target distributed parallel for some loop, same thing. The compute will be distributed evenly between two GPUs and continuously. And so in such computation where it's continuous access, well, it's good. The memory is closest to the actual processing unit. But if we are like in directions in that loop, then it means the data may be accessed through the interstack link. So now we go straight into the evaluation. So our evaluation is in two parts. First on compliance, then I'm going to talk about performance. So for compliance, we use OMDGV, that is a large test suite for compliance on the standard. It's sort of iterative with versions. There is tests for 3.0, 4.5, etc. So there is incremental tests for each version. We also tested on OVO, that is a test suite developed at Argonne by Thomas. It sort of complements the PVVs for tests on offloading hierarchical parallelism and also for math functions within target regions, like if using cosinus, sinus, SQRT. Intel allows to use that directly in target regions. So Thomas made a suite to actually evaluate if that works properly. We evaluated on 3 hardware, so the PVC Intel GPUs, and also compared with AMD and NVIDIA implementations on 300A and 800. I'm not going to go extensively through the results, so we got those two big tables. So how to read this is we got the OMPVV test per version, so it's incremental. Main idea is Intel provides whether same level of performance or higher than other vendors, most likely due to quite effort between the LCF people and Intel to have that running. On the OVO test, Intel also performed quite well in compliance. I mean, passes everything. Again, that's Thomas interacting with Intel to this result. So now on performances, we evaluated the paper 3 proxy applications, knowledge is 3D XS bench that represent different scientific computational pattern. So one is hydrodynamic simulation, one is a regular stencil over a 3-dimensional grid, the other one is a Monte Carlo transport. We again compared the three vendors with this time a bit more GPUs, so 300X as well, 800 and V100. We also evaluate the two PVC configurations where we separate tiles into different GPUs. And we measure two metrics, the computational throughput, so that the actual performances, teraflops per second, or a field of merit for Lulesh, and also the energy efficiency. So just so the next two are really clear, what here is meant by energy efficiency is the teraflop per joule. That's how much compute we are getting for a fixed amount of energy. So here are the results. On both figures, the higher the better. The left side are the gigaflops per second. Right side is the flop per watt, flop per joule. Again, I'm not going to go extensively through those results, just a few points. So that's on Lulesh that has some indirections in accesses. And so that's what we sort of observe. Oh, you're not seeing the right thing here.
No, I'm just jumping around for a second.
Yes, sir. So on that on Lulesh here we are seeing the GPU as a single big one. Here we are only using a single type of the GPU. So technically here we are only using half of the GPU because we're only using one stack. And so going from one stack to two stacks using the implicit scaling mechanism, we get 1.7 speedup on Lulesh. So ideally, we could reach 2x speedup if the compute was really competing in common. But what's happening in that case is that some memory accesses are going through the interstack link, which is a bit slower and has a higher latency than accessing the direct local HBM per stack. If we compare to 800, that is the other machine we have at Argonne Polaris, users can expect then about 10% more computational throughput, just going from one 800 to one PVC, but it's much more energy endeavor, which is shown here. Second result I'm going to show here is the result on XS Bench, so that's the Monte Carlo proxy app. We are observing this time slowdown when using the full GPU against a single time. That's this result here. Like using half the GPU leads to higher performance in this case. And again, that's due to this link. In this case, the memory is spread around the two HBM. And this application is very latency bound. There is not much compute. So just using only half the GPU is enough to get sufficient computational power and still manage to have better locality this way. So that's what we are seeing here. It's also performing surprisingly well against other vendors on that specific proxy app with a 2x speedup on a single PC stack against a full 800. So I'm going to conclude now. So the Aurora supercomputer entered production last January. Users have been working on porting their applications, some are running. I've presented evaluation on compliance and performances. Compliance using OpenMP OVO. OVO was introduced in that paper. That's work by Thomas again, but it has been developed for like 5 years. Going from Polaris to PVC, users can expect 1.1 to 2.3 speedup, but at the cost of higher energy consumption. The current recommendation we have at Aurora that is sort of confirmed by this result. I haven't gone through it, but the idea is, well, locality matters, so binding one NK process per tile is the recommendation, and this is what would give you the most performance right now. We got Intel reversing the implementation into LLVM. Alex recently opened a pull request on GitHub. That was like 2 weeks ago. So that's ongoing. About future work now, this is completely unrelated to everything I've presented right now. Over the past year, I've been working a lot on multi-GPU BLAST library, something called XKBLAST. The keynote yesterday talked about it briefly. In that library, I'm not using OpenMP because I'm using some sort of data flow with implicit coherency between tasks. So what I would need in OpenMP, that would be sort of fusing the depend and the map clause in one. So dependencies and memory movements become a single thing with some sort of runtime coherency logic that ensures minimal data movements between task scheduling across multiple GPUs. So I might at some point try to just think how can that manifest in the standard somehow, but I'm not sure I'm going to go that direction. I'm just opening it now. Other things I might do in the next year is in the coming year are the two recent clauses, task graph transparent. I believe they might significantly impact implementations if they were to be implemented efficiently. So that might be something I'll be looking at in the next year. Well, thank you very much for your attention. I'm open to questions.
Question. All right. Well, can you go back to the performance slides?
Mhm.
Either one. Yes.
Either one?
Yeah. So, I mean, there's two sources of possible differences, right? The capability of the GPUs and then how well things are actually making use of the GPUs. So on the Intel GPUs, do you think there's much headroom for improvement? And if so, like what are the, are there things that can be added to OpenMP that would enable better performance on these GPUs?
Yeah, that's something I thought of before your question, so I don't really know, honestly. I don't think there is fundamental issues right now in the OpenMP implementation from Intel. Like it's converted to Sphere based running. So no, I don't know.
Okay. There it is. All right, well, let's thank Roman again.